Folks, welcome back. This is the third installment in a series of videos I've made about working on these Radeon R9 290Xs. Now, in our previous installments, you may remember we concentrated our efforts on repairing this card here, which we're calling card A. And card A was the one that had the most obviously wrong with it, and it was the most straightforward to diagnose. You may also remember that this one, which we called card B, worked. And I couldn't obviously find anything wrong with it, but we'll get to that in a minute. First, I want to talk about card A. Now, you may remember that one of the things we did is replace some components of our memory controller rail over here, and our phase drive IC right there, in the hopes that repairing the memory controller power rail would get the card working again. But that wasn't the case. And after replacing that and confirming that the resistance to ground across the memory controller and our memory power and our vCore here were all within the range one would expect. The next suspected culprit is our IR3567B voltage controller IC, which is right here. Now, that chip has a firmware on it, which means that we can't just buy a new one and solder it on there. We would need to get one that is programmed to be on a 290X. And that's not something we can just buy. So we would need to cannibalize an otherwise working 290X in order to get that chip off. I don't have one I'm prepared to cannibalize immediately, so we're not going to do that. And furthermore, I plugged this card in to test it one more time the other day, and when I powered the system up, I heard that sickening, really faint pop sound you hear when something fails, and now we have a 60 ohm short to ground on our 8-pin PCIe power connector. So we've got 60 ohms from here to ground, and we should have thousands. Now I expect what happened is that one of these capacitors here, either these or somewhere in here, it's the first 3 or 4 phases over here, right in here. A capacitor in there, I suspect, is now shorted to ground. And if I just started removing them, eventually I would find it, and we could put the remaining ones back on and put a new one on and get it working again. At least that part. But that's a lot of work, and frankly, I just don't think I care to do that. So we're going to say for the moment that this card is dead, and we're going to use it as a donor, and we're going to move on to card B. So first, before we talk about card B, let's get card A out of the way here. All right, card B. You may remember from previously, I mentioned that this card actually works. We can plug it into the system and power the system up, and we get a picture on the screen, and in fact, we can even get into Windows and install a driver, and it works great right up until the system, until at least the card shuts off, because this VRM is overheating. Now, that happens when the MOSFETs in the VRM lose too much energy as heat, because they're not being switched properly. If they don't switch on quickly and then switch back off quickly, they kind of partially conduct and burn a whole bunch of energy off as heat. And that's why they can overheat. And that's what I think is happening in this card. Now, the reasons for that could be many, and one never knows, especially with a VRM as complex as this one that has that programmable voltage controller. But I think I figured out what the problem is. So, if we look right here, maybe I can zoom you in, hang on. Okay, if we look right here, we have a row of components that are clearly, there's one set for each phase. We've got 2 capacitors and a resistor there. We've got 2 capacitors and a resistor here, and so forth, all the way across. We actually have one more phase up here, which is for the memory power, and that doesn't have the same circuitry. But for our 5 phases of our vCore, we've got that same cluster. However, if we look right here, we'll notice that we're missing a capacitor. And that missing capacitor, I suspect, has something to do with why our card almost works. Now, what these are for, I seriously suspect, is that they are used to monitor the current being produced by each phase, with the idea being that it uses that information to balance the power being put through each phase. You want them all to be doing the same amount of work instead of one doing way more work than any of the others. But we're missing a capacitor, and I suspect that that throws off our current sense readings and causes this phase to work harder than the other ones. So what we're going to do is we're going to cannibalize the corresponding capacitor from card A, and we're going to solder it on here, and we're going to see if that fixes our problem. If it does, we've fixed the card, and we'll put a real heatsink on this with a real fan and put it on a shelf and display it and call this a victory. If not, we're going to have to do some more digging. But I've jabbered at you enough. Let's get on with preparing card A for surgery and get that old capacitor off and get a new one on here. All right, I lied. Before we take this apart and start swapping parts around, there's something I want to show you first, and that is that the performance of that phase that we suspect has a problem because of our missing cap is different from the other four. And we can do that by measuring the duty cycle of the high and low side MOSFETs on each phase. So you can see I've got the card hooked up to the test bench here. I've got my voltmeter, or my multimeter, and we're going to set the multimeter to Hertz mode, and then we hit our Hertz button, and now it's in duty cycle percent mode. So we've got our percentage here. What this represents is the percentage of the time that we have a voltage greater than 0 between our two leads. So if we go ahead and start up our test bench with the card attached, whoops. All right, can you hear that? Test bench is running, and we'll give the system a second to post, and it should. Yep, there it is. Okay, we've got a display on the monitor now, and there's no bootable drive attached, so the system's just going to sit there idling. You probably can't make this out, but we've got these 0 ohm resistors here and there. One pair for each phase driver. And what those are they're basically like a fuse on the gate pin for each MOSFET in the VRM. So if we touch one of the terminals, and first is our affected phase. Oops. Let's look here. 94%. 94%. See that? Okay. Remember that number. Now, that's the low side MOSFET on our affected phase. Now, if we look at the low side on another, 88%. As you can see, that phase is working differently than our other phases. If we look at the high side MOSFET, we see a similar story. So here is our suspect phase, 6-ish%, and here is a suspected good, 10-ish%. So the high side MOSFETs are working quite a bit differently on our good phases than our bad one. And so what we're seeing there is that the high side MOSFETs are on for a much longer period of time, and our low side MOSFET on our affected phase is on for a longer period of time than the others. And that can have a profound impact on the thermal performance of your MOSFETs. So that's one example of a way that we can check this before we just start taking stuff apart. Anyway, enough jibber jabber. Let's see if we can't get this fixed. Okay, so we'll set our multimeter aside here and set card B aside. We'll grab card A, which is our donor. We need to get our capacitor. Maybe if we do it this way. How about this way? That'll work, I think. Okay, so our capacitor that we need to remove is right there. So let's get our RR station ready. Right, also turn on our soldering iron. Get a little flux on there. Alright, so we just heat our part of the board there till the solder melts. We can pull our cap off. Okay, at length, we got our tiny little cap off that there's no way you're going to be able to see that, but I've got it here stuck to my tweezers. Before we attach that to the new board, or the patient board, let's get this guy out of the way. I want to measure its capacitance to find out exactly what the capacitance of this is supposed to be, just in case we have to go get some new ones. So it looks to me like the patient board just had it knocked off. Maybe something got dropped on it. Okay, let's, so, shoot, what did I do with it? There it is. Okay, right there. So, before we, attach it to our new solder it in place on it in its new home, let's see, where's capacitance? There it is. Okay. Okay, so we've got our tiny capacitor here, and there's probably no way you're going to be able to see that in the video, but you'll have to trust me it's there. So we touch our probes to it. We wait for our multimeter to stabilize. Okay, 252.4 nanofarads. So 250 nanofarads is about what we're looking at for this capacitor. Okay, now we can get the recipient board ready and get it on there. So we're going to take this guy, move it over here. It's stuck to my tweezers. So we need to take our recipient card, and we need to get the heatsink off of this in order to be able to solder anything onto it. With the heatsink on there, there's no way we're going to get this hot enough. When I put this heatsink back on it, for testing purposes, I didn't use all of the screws. It just needed to kind of not fall off. So we will eventually put it on there properly. But if you're wondering why I don't have a screw in every hole, well, that's why. Okay, there we go. So we got our heatsink, which we will set aside. We've got our capacitor. Now, how do we want to do that? I think I guess we'll use hot air. Before we do that, actually, we need to clean up the pads. So, the spot that it goes is right here. Put a little flux there. We need to use our soldering iron to make sure that if there's any remains of the old capacitor still on there, we've cleaned it off. Let's turn this way. We're going to clean the old solder off with some solder wick before we put on new. Just to make sure we've got clean pads. There we go. Tin our iron. There we go. All right, now comes the tricky part. It actually may be easier to use the hot air station for this. Shoot, I hope I didn't damage the capacitor. Yeah, I think we're going to have to use hot air for this. There it is, approximately. Okay. Now, fire up our hot air station here. Okay, so our capacitor is still looking okay. So let's get in there like this, kind of on our pads. Hit the board. There we go. On the pads, heat removed. Okay, there we go. Now, let's turn this off. Now, we need to let the board cool down. One of the things that we're trying to fix is a problem where the board overheats. So if we start with it hot, we'll never know whether or not we got the problem fixed. So I'm going to clean the soldering iron off and shut it off. And we'll put the heatsink back on enough that the board won't melt itself. And we'll see if this actually fixed our problem. Fingers crossed it did. Anyway, I'm going to go have a coffee or something, and I'll be back in 20 minutes once this has cooled down to room temperature. Alright, a few minutes have passed, and our board has cooled down to room temperature. So we're ready to put the heatsink back on it. And we just need to get the heatsink on there well enough that it's cooling the MOSFETs so they don't melt themselves. We don't have to put all of the screws in, we just need a few. So we'll do like a couple for the core, and these two here for the, and maybe that one. So we got our heatsink back on there. Now, let's grab our multimeter here. And remember the test I showed before, where we measured the duty cycle on our MOSFETs? Now we'll do the same test once more and see if our duty cycle on our, whatever this phase is, it's either 1 or 5. I'm not sure which way they go. But we'll see if the duty cycle on our MOSFETs there is now back in line with the others. So let's go ahead and plug it in. All right, set this to duty cycle mode. Okay. All right. Cross your fingers, folks. Power supply on. Fingers crossed. All right. All right, so we've got a post. 8.9. 89.4. Look at that. See that? So those are at 90%, and these are about 9%. And if we put our finger on it, yeah. By now, right there would have been really hot. But it's not. This is cool to the touch. So, I think we've fixed our problem. The next step is to clean the flux residue off of the card and put a heat sink on it for real with a fan and maybe get into Windows and see if we can install a driver. We want to be careful about just like hitting it with full load right out of the gate, because if you haven't fixed the problem, you can damage stuff worse if you do that. But this is looking promising. We're not getting so hot that you can't touch it, and oh yeah, that's definitely better. So yeah, I'm gonna go ahead and clean this now, and we'll reconvene in just a minute once I'm done. Alright folks, I took my time cleaning and reassembling the card, and as you can see, I used card A's blower heatsink here, as opposed to card B's, whatever the not blower heatsink, because I don't have the fans from it. But as you can see, we've got the card reassembled and plugged into the test bench, and GPU-Z is working just fine. I'm not running Heaven at the moment because I'd have to talk over the fan then, and these blower heatsinks are notoriously loud. But the card works just fine. It gets through the Heaven benchmark totally fine, other than being noisy. And it scores about a 25 or 2600, which I think is a little bit low for a 290X, but the CPU in this machine isn't terribly fast. I have a feeling that has something to do with it. Anyway, a little bit of card A will live on in card B, given that we had to cannibalize not only its heatsink, but also some of its capacitors. But unfortunately, I think card A may just be beyond saving. As you may recall, I talked about how the controller on card A requires a firmware that we'd have to get from somewhere else. About the only place I could be able to get that is card B. And I'm not cannibalizing card B since it works. And one last thing that I wanted to mention. I had to replace two other capacitors on card B that I also got from card A, but they're kind of in this area. And one of the things I noticed was that all of the damage, and the reason I suspect it didn't work, is parts were broken off of the back. And I can't help but wonder if that's the reason that graphics cards now, especially given how much more complex they are, I can't help but wonder if the reason that's why they come with metal backplates, as opposed to just an exposed PCB like this. It seems like for what the metal backplates cost to include, which can't possibly be more than a couple of dollars, the manufacturers must be saving quite a bit in terms of warranty claims and just the hassle of dealing with disgruntled customers who had stuff break off of the card, and then they try to send it back for a warranty service and it gets denied. Anyway, that's just a thought that I had as I was working on this, that I wonder if that's why they have these metal backplates. Anyway, I hope this has helped you out, or at least been entertaining. And as always, I'll see you in the next one.